Nonlinear regression. Nonlinear regression in terms of variable in the first equation. For example, that is yt is equal to alpha plus beta 1 x1t plus beta 2 x1t square plus beta 3 x1t cube. Here, non-linearity in terms of variable. Variable means x and y are the variables and alpha and beta are the parameter. Y, it's a dependent variable, x is an independent variable. Uh, there is some terms like x power 1, x power 2, x power 3. That is why it is called non-linear in terms of variable. Non-linear in terms of nonlinear in terms of parameter. That means y is equal to alpha 1 e power beta 1 x1 plus alpha 2 e power beta 2 x2 plus epsilon. Here alpha and beta are the parameter term. E power beta 1 x1, beta is a parameter. E power beta 2 x2, beta is parameter into variable plus epsilon. If the equation is nonlinear in terms of variable, it can be linearized in this way, like yt equal to alpha plus beta 1 x1t plus beta 2 x1t square plus beta 3 x1t cube. That can be written as in this line beta alpha plus beta 1 z1t plus beta 2 z2t plus beta 3 z3t. Y is equal to a Cobb-Douglas production function beta k power alpha L power beta. If it takes the log transformation, it can be linearized. This type of model which are suitable transformation can be linearized, known as intrinsically linear model. This model, if this type of Cobb-Douglas type of nonlinear model can be linearized, then it is called intrinsically linear model. But if we have nonlinear in terms of parameter and any sort of transformation, this type of model cannot be trans into linear. So these are known as intrinsically nonlinear model. That is this is a nonlinear model. So when in terms of parameter and this transformation cannot be linear, so this is known as intrinsically nonlinear model. Estimation of the nonlinear model. In this type of estimation, sum of square error function is evaluated for alternate set of coefficient. Those values which results in minimum square error are chosen are the estimates. This method is effective only when one of two coefficient is estimated. That means the sum of the square error function is evaluated only for alternate set of coefficient. Those values which result is minimize the squared error, that is chosen only when one or two coefficient is estimated. Suppose yi equal to alpha naught plus alpha 1 x1 I power beta 1 plus alpha 2 x2 I power beta 2 plus epsilon I. Or we can write in this way that y is a function of x variable and the parameters plus epsilon. F is a nonlinear function with k independent variable. K its x is uh, xi. Here I is equal to 1 to k. The criteria used to determine the estimate value for the coefficient is that we try to minimize sum of the square error. So our objective is to minimize the sum of the square error. If we have row observation, here consider k number of beta and k number of x variable and row number of parameters. So if we have row observation, then we can write sum of the square error in this way, that is uh, S is the sum of the square error in the nonlinear model, but we know that in the ordinary least square technique, sum of the square error is estimate actual y minus estimated y whole of square. Here beta are the estimated beta. S is sum of the square error in the Wales, actual minus estimated in Wales. But in the nonlinear case, we can write in this way, that is actual output minus estimated I already written here in this page. So we call this beta 1 hat, beta 2 hat, beta rho hat. It's the nonlinear least square estimated of beta 1, beta 2 up to beta rho that minimize the value of S. However, if more than two coefficients are involved, an extremely large number of calculation done, so the method become computationally very expensive. For example, if there are 4 coefficients and 20 alternative value for each coefficient, the procedure will be very cumbersome. That is why we consider direct approach. The parameter estimates are obtained here by differentiating sum of the square error function with respect to each coefficient. The derivative equal to 0 and solving the result of the set of the normal equation, which are called the normal equations. Taking derivative of the sum of the square error in the nonlinear model, uh, So write down the equation first. That is S is equal to sum of t equal to 1 to t minus 1 to t, third bracket, yt minus f of x1t comma x2t comma up to xkt, and row number of parameter, that is row 1, row 2, row 3 up to row beta 1, beta 2, beta 3 up to beta row, whole bracket square, with respect to beta 1, beta 2, beta 3, beta row, and setting them equal to 0, we find the normal equation are taking derivative with respect to beta. That is why we get sum of t equal to 1 to t 2 yt minus f of x1t, x2t, x3t, xkt, beta 1, beta 2, beta 3, beta row, del f by del beta I, it's equal to 0 for here for all I equal to 1 to row. This non-linear equation must be solved simultaneously for beta 1, beta 2, beta 3 and beta row. Since each equation may contain all row coefficient, one variation of the approach is that computationally steepest descent method. The method works by moving from one trial set of coefficient value for beta 1, beta 2, beta 3 up to beta row to the new set in such a way that minus del S beta 1, comma minus del S beta 2 up to minus del S beta row as large as possible, resulting is rapid progress to the value of beta 1, beta 2, beta row that minimize is. So here our objective is we choose beta 1, beta 2, beta 3 in such a way that del S divided by del beta I will be minimized. That is why we provide minus sign here. That means value is minimum. This is the third approach. It's to solve the nonlinear equation process, estimation process. It's iterative linearization method in which nonlinear equation is linearized around some initial set of coefficient value. Whereas is performed on the linear equation generating a new set of coefficient value. The nonlinear equation is relinearized around its new coefficient value. Whereas is again performed to generate new coefficient value, and equation is relinearized around value. This iterative process is repeated until convergence coefficient value do not change substantially. That is, until the coefficient value do not change substantially after each new Wallace, this approach has certain advantage. The equation to be first advantage is this is the first advantage. Only this portion. This approach has certain advantage. The equation to be estimated is closely approximated by a linear equation. Very few iterations are necessary. The second approach is that advantage is that the second advantage provides clear guidance for being statistical tests that usually apply to linear regression. Since linear regression is preferred to each iteration, one can use statistical test, R square t test, to evaluate the fit of the final linearized estimation equation. we use the fact that any nonlinear function can be expressed as a Taylor series expansion. Especially, we can write y equal to f of x1, x2, xj up to xk, beta 1, beta 2, beta 3, up to beta k plus epsilon in an expression around a set of initial value beta 1, 0, beta 2, 0, beta rho 0. So here we can write beta 1 is equal to beta 1 naught, beta 2 equal to beta 2 naught, beta rho equal to beta rho naught in this way. So here y it's equal to f of x1, x2, x3, xk, beta 1, 0, beta 2, 0, beta rho 0 plus sum of I is equal to 0 to rho del f by del beta 1 bracket 0, or we can call it uh, not 0, or sum of I equal to 0 to rho del f del beta 1 not first bracket beta I minus beta I 0 plus 1 by 2 sum of I equal to 1 to rho sum of j equal to 1 to rho. The second order condition del 2f del beta I del beta j, beta I beta minus beta I 0 beta j minus beta j 0. Now the subscript 0 on the partial derivative denotes the derivative 1 evaluated, that beta 1 it's equal to beta 1 0, beta 2 equal to beta 2 0, beta 3 equal to beta 3 0, or beta rho equal to beta rho not 0 or not. We can consider as not. A linear approximation of our nonlinear function to be provided by the first two terms on the Taylor series expansion. Dropping the second and higher order term, we can write in this way here y equal to f of x1, x2, x3 up to xk, or beta 1 naught, beta 2 naught, comma up to beta rho naught plus sum of I equal to 0 to rho beta 1 beta I 0. First order condition del f by del beta I it's equal to sum of I equal to 0 to rho beta I into del f by del beta I naught plus epsilon. From this equation actually we just drop the second order derivative and setting the first order condition is equal to 0, and we can show that all f term is here plus summation term is there into beta I, and the other term is placed in the right hand side. So this term we can take into the right hand. this line. So observe the regression 3. This can be named as 3. Observe the regression 3. We have a linear equation. Left hand side is the constructed dependent variable. Right hand side consists a additive term, a set of unknown coefficients. These are beta 1, beta 2, beta 3, beta rho, multiplying a set of constructed independent variable. So equation 3 can be estimated by Wallace. The estimated coefficient now be leveled at beta 1 1, beta 2 1, beta 3 1, beta rho 1. The estimated coefficient value are leveled as beta 1 1, beta 2 1, beta rho 1, and there are new set of initial estimates and non-linear equation as relinearized around this new set of values, and the result of new linear equation y is equal to f of x1 comma x2 up to xk comma beta 1 1, beta 2 1, beta 3 1, beta 4 1 up to beta rho 1 plus sum of I equal to 0 to rho. Here beta 1 1, beta 2 1, beta 3 1, beta rho 1 plus sum of I equal to 0 to rho beta I first order condition, change f due to change of beta 1 is equal to sum of I equal to 0 to rho beta I del f by del beta I plus epsilon. Also again OLS applied a new set of coefficient estimate beta 1 to beta 2 to beta 2 3 beta 3 to beta 4 to beta rho 2 are obtained. This process of relinearize is repeated until convergence occur. So here beta I j plus 1 minus beta ij divided by beta ij. This is mod, it's less than lambda. Here I equal to 1 to rho, lambda it's a small number whose choice depends upon the computational expense. So the process is repeated in this iterative linearization method. We obtain the parameter in such a way, and the process of relinearization is repeated until convergence occurs.